Hello guys, and welcome to Deep Cosmos. Tonight, we embark on a journey that begins with the most profound question in science, and perhaps the most humbling one we can ask. This exploration reaches far beyond the boundaries of human experience, into the deepest wells of time itself, where the answers lie not in what we can observe today, but in what happened when our planet was utterly alien to everything we know about life. This isn't just about the past, it's about the vast mystery that surrounds every breath you take, every heartbeat, every thought crossing your mind right now. Because somewhere in the incomprehensible depths of 4 billion years ago, something impossible happened. Non-living matter became alive, and it all began with water. The question that haunts every scientist who dares to peer into these ancient mysteries is staggering in its simplicity, yet devastating in its complexity. How did the universe learn to think about itself? How did atoms that had swirled in cosmic darkness for billions of years suddenly organize themselves into something that could wonder, could feel, could dream? We know the outcome. We are living proof of it. Every creature that has ever drawn breath, from the smallest bacteria to the largest whale, from the first stirring of consciousness in primordial pools to the moment you became aware that you exist, all of it traces back to one extraordinary chapter in our planet's history, the birth of the first oceans. But knowing the outcome doesn't diminish the mystery. If anything, it deepens it, because when we follow the evidence backward through time, when we peel away layer after layer of Earth's history, we arrive at a moment so improbable, so against every expectation of physics and chemistry, that it borders on the miraculous. In laboratories around the world today, scientists are attempting something that might seem like playing God. They're trying to recreate the origin of life itself. They mix the same chemicals that swirled in Earth's primordial seas. They recreate the temperatures, the pressures, the atmospheric conditions of a world 4 billion years younger. And occasionally, just occasionally, they witness something extraordinary. Molecules that begin to behave as if they're alive. But here's what stops them cold, what fills them with both wonder and frustration. They can create the conditions, they can nudge chemistry toward biology, but they cannot yet solve the central riddle. They cannot explain why it happened here, why it happened when it did, and perhaps most mysteriously of all, why it happened at all. The story we're about to tell is written in stone older than mountains, in chemical signatures buried beneath. Miles of sediment in the very composition of the water that flows through your veins right now. It's a detective story where the crime scene is 4 billion years old, where the witnesses are rocks and minerals, and where the evidence points to an event so unlikely that mathematicians struggle to calculate its probability. Yet it happened. Against all odds, in defiance of entropy and chaos, something stirred in Earth's first oceans that had never existed before in the 10 billion year history of our universe. Something that could grow, that could change, that could pass its secrets from one generation to the next. Something that carried within itself the spark of every song that would ever be sung, every discovery that would ever be made, every moment of love that would ever be felt. This is the story of how water learned to dream, how simple molecules discovered the secret of complexity, how death gave birth to life, and how that life would go on to transform not just our planet, but our entire understanding of what's possible in a universe that seemed destined for nothing but cold, empty darkness. The answers we're seeking stretch across scales of time and space that challenge human comprehension. They require us to imagine a world where the sky was orange, where the oceans were green, where the very air would have killed us instantly. A world where the greatest storms in Earth's history raged for millions of years, where asteroids fell like rain, where the ground itself was molten and angry. And yet in that chaos, in that violence, in that seemingly hostile cosmos, the most delicate, most intricate, most beautiful process in the known universe began to unfold. Life learned to live, and water was its teacher, its cradle, its first and eternal home. The journey we're about to take will carry us backward through time to witness events that dwarf anything in recorded history. We'll stand on the shores of seas that no human eye has ever seen, breathe air that existed before breath itself was invented, and watch as the fundamental forces of nature conspired to create something unprecedented, a planet where rocks could learn to love. But our story doesn't end in the past. It flows like an unbroken river from those first stirrings of life to the moment you opened your eyes this morning. Because every drop of water in your body, every molecule that keeps you alive, carries within it the memory of those first oceans. You are not just observing this story, you are its continuation, its current chapter, its living proof that the impossible can become inevitable. So join us now as we dive deeper than any submarine has ever traveled, not through space but through time itself, to discover how water created life, how life created consciousness, and how consciousness created the capacity to look back across 4 billion years and ask the question that started it all: how did we come to be? The answers lie waiting in the depths of time, in the memory of water, in the vast unknowns that remain, waiting to be uncovered. To understand how life began, we must first travel to a place where life was not just impossible, it was inconceivable. We must venture back 4.6 billion years to a time when our solar system was nothing more than a swirling disk of dust and gas, heated by the violent birth cries of our young sun. Imagine, if you can, a cosmos where the very concept of Earth doesn't exist, where instead of our blue marble suspended in space, there's only chaos, countless fragments of rock and ice colliding, merging, destroying each other in an endless dance of cosmic violence. The temperature in this stellar nursery reaches thousands of degrees. Any water that might have existed is instantly vaporized, blown away by solar winds so powerful they reshape the architecture of worlds. This is the Hadean Eon, named after Hades itself, a hellish period that makes the most extreme environments on modern Earth seem like gentle gardens. And yet, from this inferno, our story must somehow begin. The Earth that's forming in this cosmic storm bears no resemblance to the world we know. There are no oceans because there is no water. There is no atmosphere because there are no mechanisms to hold gases close to the surface. There are no continents, no mountains, no valleys, just a molten ball of rock being constantly reshaped by impacts so massive they vaporize entire regions of the planet's surface. Every few million years, sometimes more frequently, asteroids the size of mountains slam into this proto-Earth with the force of billions of nuclear weapons. Each impact releases enough energy to melt the planet's crust all over again. The surface temperature hovers around 100-200 degrees Celsius, hot enough to melt copper, hot enough to turn rock into flowing rivers of magma that stretch from horizon to horizon. But here's what makes this period so crucial to our story. This apparent destruction is actually construction. Each collision, each merger, each violent reshaping of the planet's surface is adding mass, adding complexity, adding the raw materials that will eventually become the stage upon which life performs its first act. Modern scientists studying this period face an extraordinary challenge. They're trying to understand events that happened before most of the evidence could survive. The rocks from this era have been recycled through Earth's interior so many times that finding direct witnesses to the Hadean is like searching for individual raindrops in an ancient storm, yet they persist because buried in the few surviving. Minerals from this epoch are clues to one of the most important questions in planetary science. When did Earth become capable of holding water? The answer lies in understanding something called the Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system experienced a renewed surge of catastrophic impacts. During this cosmic shooting gallery, Earth was struck by asteroids and comets so frequently that the planet's surface was repeatedly sterilized, any complex chemistry wiped clean and forced to start over. And yet, paradoxically, this same bombardment was delivering something precious. The ingredients for oceans. Many of these cosmic projectiles weren't just rocks. They were massive chunks of ice, frozen reservoirs of water that had formed in the cold outer reaches of our solar system. With each impact, they were making a delivery that would change everything. But the timing had to be perfect. Too early, and the water would boil away in the hellish heat. Too late, and the bombardment would end before enough water accumulated. Earth needed to cool just enough, and the impacts needed to continue just long enough for the impossible to become inevitable. As we piece together this ancient story from meteorite fragments, from computer simulations, from the faint chemical signatures preserved in the oldest minerals on Earth, a picture emerges of a planet in transition. The Hadean Earth was not just a world being destroyed, it was a world being prepared. Every impact, every reshaping of the surface, every addition of cosmic debris was setting the stage for something unprecedented in our solar system's history. The violence was slowly giving way to chemistry. The chaos was organizing itself into the first crude systems that could hold complexity. The temperature was dropping degree by precious degree toward a range where molecules could survive long enough to interact, to combine, to build the foundations of something more. By the end of this primordial epoch, roughly 4 billion years ago, Earth had achieved something remarkable. It had become capable of keeping secrets. The surface was finally cool enough for water to exist as a liquid, at least temporarily. The atmosphere was beginning to thicken, creating pressure that could hold gases close to the surface. The bombardment was slowing, giving complex chemistry time to unfold without being constantly reset by catastrophic impacts. But Earth still had no oceans. The water was coming. Indeed, it was already arriving with each icy comet that survived the journey from the outer solar system. But accumulating enough water to fill the basins that would become our oceans would require something extraordinary. The right balance of impacts, cooling, and atmospheric development happening simultaneously. What was about to unfold over the next few 100 million years would transform our planet from a hellish wasteland into something that had never existed before in our solar system, a water world. But that transformation would require Earth to thread a cosmic needle to achieve conditions so precise that modern climatologists still debate whether it was inevitable or miraculous. The stage was set. The ingredients were being delivered. The temperature was approaching the critical threshold where water could survive on the surface. But the greatest challenge still lay ahead. How could a planet learn to hold oceans? How could water, arriving drop by precious drop from cosmic ice, accumulate into the vast seas that would become life's cradle? The answer to that question would determine not just Earth's future, but the future of consciousness itself. Because without oceans, there could be no laboratory vast enough, stable enough, complex enough for the experiments in chemistry that would eventually learn to think. The chaos was organizing itself into the first crude systems that could hold complexity. The temperature was dropping, degree by precious degree, toward a range where molecules could survive long enough to interact, to combine, to build the foundations of something more. By the end of this primordial epoch, roughly 4 billion years ago, Earth had achieved something remarkable. It had become capable of keeping secrets. The surface was finally cool enough for water to exist as a liquid, at least temporarily. The atmosphere was beginning to thicken, creating pressure that could hold gases close to the surface. The bombardment was slowing, giving complex chemistry time to unfold without being constantly reset by catastrophic impacts. But Earth still had no oceans. The water was coming. Indeed, it was already arriving with each icy comet that survived the journey from the outer solar system. But accumulating enough water to fill the basins that would become our oceans would require something extraordinary. The right balance of impacts, cooling, and atmospheric development happening simultaneously. What was about to unfold over the next few 100 million years would transform our planet from a hellish wasteland into something that had never existed before in our solar system, a water world. But that transformation would require Earth to thread a cosmic needle to achieve conditions so precise that modern climatologists still debate whether it was inevitable or miraculous. The stage was set. The ingredients were being delivered. The temperature was approaching the critical threshold where water could survive on the surface. But the greatest challenge still lay ahead. How could a planet learn to hold oceans? How could water, arriving drop by precious drop from cosmic ice, accumulate into the vast seas that would become life's cradle? The answer to that question would determine not just Earth's future, but the future of consciousness itself. Because without oceans, there could be no laboratory vast enough, stable enough, complex enough for the experiments in chemistry that would eventually learn to think. Modern astrobiologists studying this period are struck by a profound realization. The water in Earth's oceans has been recycling through the planet's systems for 4 billion years. Every glass of water you drink contains molecules that have been ocean, cloud, rain, river, and living tissue countless times. Some of those molecules were present when the first life forms stirred in primordial seas. You are not just made of water. You are made of the same water that witnessed the origin of life itself. Your body carries the memory of those first oceans, encoded in the chemical composition of every cell, preserved in the salts that keep your nerves firing and your heart beating. The stage was nearly set. Water from the void had found its way to Earth. The planet had learned to hold this precious cargo despite cosmic violence that should have made such accumulation impossible. The temperature was dropping toward the critical range where liquid water could persist. The pressure was building toward levels where complex chemistry could unfold. But the greatest transformation still lay ahead. These scattered pools and primitive seas were about to become something they had never been before, a laboratory vast enough and stable enough for the universe's most ambitious experiment, the creation of life from lifeless matter. Modern astrobiologists studying this period are struck by a profound realization. The water in Earth's oceans has been recycling through the planet's systems for 4 billion years. Every glass of water you drink contains molecules that have been ocean, cloud, rain, river, and living tissue countless times. Some of those molecules were present when the first life forms stirred in primordial seas. You are not just made of water, you are made of the same water that witnessed the origin of life itself. Your body carries the memory of those first oceans, encoded in the chemical composition of every cell, preserved in the salts that keep your nerves firing and your heart beating. The stage was nearly set. Water from the void had found its way to Earth. The planet had learned to hold this precious cargo despite cosmic violence that should have made such accumulation impossible. The temperature was dropping toward the critical range where liquid water could persist. The pressure was building toward levels where complex chemistry could unfold. But the greatest transformation still lay ahead. These scattered pools and primitive seas were about to become something they had never been before, a laboratory vast enough and stable enough for the universe's most ambitious experiment, the creation of life from lifeless matter. Each raindrop is a messenger carrying dissolved gases from the atmosphere, minerals leached from volcanic ash, and the chemical signature of a world in transition. As the water strikes the cooling rock, it immediately begins the process that will reshape Earth's surface, erosion. For the first time, moving water begins carving channels, creating the first rivers, the first valleys, the first pathways toward the low places where oceans will form. But this is erosion, unlike anything on modern Earth. The rain is hot, acidic, from dissolved carbon dioxide and volcanic gases, and chemically aggressive in ways that would dissolve most rocks in days rather than millennia. The runoff carries enormous concentrations of dissolved minerals, iron, magnesium, calcium, phosphorus, all the raw materials that will become essential for life, but in concentrations that would be lethal to any living system we know, modern. Geologists studying this period face an extraordinary puzzle. They can calculate how much water vapor was in the early atmosphere, they can estimate the rate of cooling, they can model the atmospheric pressure and temperature. But when they run the numbers, they arrive at a startling conclusion. The first rains should have delivered far more water than could fit in the ocean basins that existed at the time. The answer lies in understanding that Earth's topography 4 billion years ago bore no resemblance to the world we know. There were no continents in the modern sense, no deep ocean basins, no complex system of mountains and valleys. The surface was relatively flat, covered by a thin crust that was still cooling and solidifying from the planet's molten youth. As the great rains continued, something remarkable happened. The weight of accumulating water began to press down on the cooling crust, while the erosive power of flowing water carved ever deeper channels and basins. The planet's surface was being sculpted in real time, shaped by the very water it was trying to hold. This was feedback on a planetary scale, water creating the containers that would hold more water, which would create deeper containers, which would enable even more water to accumulate. Earth was learning to hold oceans by the simple act of having water flow across its surface. But the story becomes even more extraordinary when we consider what was happening beneath the surface. The cooling crust was contracting, cracking, creating vast fissures that reached deep into the planet's interior. Some of the rainwater was disappearing into these cracks, only to encounter the still molten rock below, flash into steam, and erupt back to the surface, carrying even more dissolved minerals. This underground circulation system created something unprecedented, a global laboratory where water and rock could interact at every temperature and pressure imaginable. Minerals were dissolved, transported, precipitated, and redissolved in cycles that lasted thousands of years. Chemical combinations that had never existed before were forming, breaking apart, and reforming in new configurations. Yet gradually, over millions of years, the system began to stabilize. The rain continued, but less violently. The surface continued cooling, but more gradually. The circulation of water between surface and interior continued, but with decreasing temperature and chemical intensity. Earth was settling into the patterns that would define it for the next 4 billion years. And then, somewhere around 3.8 billion years ago, something unprecedented happened. The rain began to accumulate faster than it evaporated. Pools became ponds. Ponds became lakes. Lakes began to connect into vast inland seas. The ocean basins, carved by millions of years of erosion and weighted down by millions of years of accumulated water, began to fill. For the first time in Earth's history, there was liquid water on the surface that stayed liquid. Not for hours or days, but for years, decades, centuries. The first permanent bodies of water were forming, small and scattered at first, but growing and connecting as the great rains continued their planet-shaping work. These early seas were nothing like modern oceans. They were hot, perhaps 70 degrees Celsius on average. They were shallow, rarely more than a few hundred meters deep. They were chemically extreme, acidic, mineral-rich, and constantly changing as new water and new dissolved materials arrived with each rainfall, but they were stable. For the first time in Earth's violent history, there were environments where Complex chemistry could unfold over extended periods without being reset by cosmic impacts or volcanic catastrophes. The stage was finally set for something extraordinary, chemistry that could persist long enough to become complicated, complicated enough to become organized, organized enough to become life. The transformation was complete. What had begun as scattered water vapor in a hellish atmosphere had become the first oceans, vast, stable laboratories where the universe was about to conduct its most ambitious experiment. The water had found its home, and that home was about to become something unprecedented in the known cosmos, a place where molecules could learn to live. Water seems so ordinary, so commonplace, that we rarely pause to consider what makes it extraordinary. Yet the molecule H2O possesses a collection of properties so unusual, so perfectly suited for complex chemistry, that some scientists argue it borders on the miraculous. To understand how life began, we must look beyond water as simple liquid and see it as nature's most sophisticated chemical workshop, a molecular environment where the impossible becomes inevitable. In laboratories around the world today, researchers are discovering that water is far stranger than we ever imagined. At the molecular level, it behaves less like a simple liquid and more like a dynamic network, constantly forming and breaking connections in patterns that seem almost purposeful. Each water molecule reaches out to its neighbors through invisible bonds, creating temporary structures that last mere trillionths of a second before dissolving and reforming in new configurations. This molecular dance gives water properties that shouldn't exist. It's one of the only substances on Earth that becomes less dense when it freezes, a quirk of physics that means ice floats, keeping oceans liquid even during the planet's coldest periods. It can dissolve more different substances than any other liquid, earning it the title of universal solvent. And it can absorb enormous amounts of heat without dramatic temperature changes, creating stable environments where delicate chemistry can unfold. But here's where water becomes truly extraordinary. It doesn't just enable chemical reactions, it actively participates in them. Modern quantum chemistry has revealed that water molecules can help other molecules find each other, hold them in the right orientation for reactions to occur, and even provide the energy needed for complex transformations. Water is not a passive stage for life's chemistry, it's an active collaborator. Consider what happens when you dissolve salt in water. To our eyes, the salt simply disappears, but at the molecular level, something remarkable occurs. Each grain of salt is torn apart by water molecules that surround individual sodium and chlorine atoms, holding them in a cage of hydrogen bonds. The salt doesn't just dissolve, it becomes part of water's molecular network, creating new possibilities for chemistry that neither substance could achieve alone. This dissolving power was crucial in Earth's early oceans. As the first rains fell and the first rivers flowed, they carried dissolved minerals from every rock they touched. Iron, magnesium, phosphorus, sulfur. All the elements that would become essential for life were being concentrated in the growing seas, held in solution by water's molecular embrace. But water's most remarkable property may be its ability to organize itself. Recent discoveries in physics have shown that water molecules can form temporary structures, clusters, chains, and even cage-like arrangements that persist for microseconds before dissolving back into the random flow of liquid. These structures create microenvironments within water, tiny pockets where different types of chemistry can occur simultaneously. Imagine the early oceans not as uniform bodies of water, but as three-dimensional tapestries of constantly changing chemical environments. In one microscopic region, conditions might favor the formation of simple organic molecules. A few molecular distances away, different conditions might allow these molecules to link together into longer chains. And in yet another pocket, the chemistry might be perfect for testing whether these chains can make copies of themselves. This is where modern research becomes truly fascinating. Scientists studying the origin of life have discovered that water doesn't just make life's chemistry possible, it makes it probable. The random motions of molecules in liquid water, combined with water's ability to concentrate and organize dissolved substances, creates what researchers call emergent complexity. Simple ingredients naturally organize themselves into more complex structures, which organize into even more complex systems in a cascade of increasing sophistication. Dr. Sarah Chen, working at the frontier of astrobiology research, describes it this way. Water is like having millions of tiny laboratories operating simultaneously. Each one is running slightly different experiments, testing different combinations, exploring different possibilities. Most experiments fail, but in a system this vast, with this many simultaneous trials, even highly unlikely successes become statistically inevitable. But water's role in life's emergence goes deeper than just chemistry. It also provides the perfect environment for information to be stored and transmitted. The same hydrogen bonding that makes water an excellent solvent also allows complex molecules to maintain their shapes in solution. Proteins can fold into precise configurations. DNA can maintain its double helix structure. RNA can form the intricate shapes needed to catalyze reactions, all because water provides just the right balance of stability and flexibility. Modern quantum physics has revealed an even more extraordinary aspect of water's behavior. At temperatures near those of Earth's early oceans, water molecules exist in a state of quantum coherence. They can occupy multiple states simultaneously, allowing them to test multiple chemical pathways at once. It's as if each water molecule is running parallel experiments, exploring different possibilities before collapsing into the most favorable outcome. This quantum behavior helps explain one of the great mysteries of life's origin: how the right molecules found each other in the vast dilution of early oceans. Traditional chemistry suggests that the concentrations of organic molecules in primordial seas were far too low for complex reactions to occur. But water's quantum properties, combined with its ability to concentrate and organize dissolved substances, create islands of higher concentration where chemistry can flourish. The implications stretch far beyond Earth. As we search for life elsewhere in the universe, we consistently look for signs of liquid water. Not because we lack imagination, but because we're beginning to understand that water's properties are not just helpful for life, they may be essential. The delicate balance of stability and reactivity, of solvent power and structural support, of thermal regulation and information preservation may be impossible to replicate with any other substance. Yet even as we celebrate water's extraordinary properties, we must remember that the early oceans were nothing like the water we know today. They were hotter, more acidic, richer in dissolved minerals, and subjected to radiation levels that would destroy most modern biological molecules. The question that haunts origin of life researchers is profound. How did life's delicate chemistry emerge in such harsh conditions? The answer may lie in water's greatest gift to early life: protection. Even in the extreme conditions of primordial oceans, water provided a buffer against the worst of Earth's violence. It absorbed excess heat, diluted toxic chemicals, and shielded fragile molecules from harmful radiation. Within the molecular embrace of liquid water, chemistry had its first safe haven, not perfect protection, but enough shelter for the first experiments in complexity to unfold. And those experiments were already beginning. In the mineral-rich waters of Earth's first oceans, something unprecedented was stirring. Simple molecules were finding each other, connecting, forming chains and networks of increasing sophistication. The universal solvent was about to become something even more remarkable: the medium in which lifeless matter would cross the threshold into life. You are not just made of water, you are made of water's possibilities made manifest. And those possibilities first stirred to life in alien seas under an orange sky 4 billion years ago, when molecules began their first tentative experiments with organization, complexity, and the radical idea that matter might learn to live. In the warm, mineral-rich waters of Earth's first oceans, something extraordinary was beginning to unfold. For nearly 200 million years, simple molecules had been bumping into each other in random encounters, occasionally sticking together before drifting apart again. But around 3.8 billion years ago, these chance meetings began to develop into something more deliberate, more organized. Chemistry was learning to choreograph itself. To understand what was happening, we must shrink ourselves down to the molecular level and witness events that no human eye could ever see. Picture yourself floating in these ancient waters, surrounded by a soup of simple compounds: methane, ammonia, hydrogen sulfide, and carbon dioxide dissolved from the thick atmosphere above. Lightning crackles through the orange sky, sending energy cascading through the water. Volcanic vents on the seafloor pump out minerals and heat, creating currents that stir this chemical broth in endless, complex patterns. At first glance, it appears to be chaos. Molecules collide billions of times per second, most encounters lasting mere nanoseconds before the participants separate and drift away. But within this apparent randomness, patterns are beginning to emerge. Certain molecules have shapes that fit together like puzzle pieces. Others have electrical charges that attract their opposites. Some have the ability to catalyze reactions, to help other molecules connect while remaining unchanged themselves. Modern biochemists studying this period have made a remarkable discovery. The chemistry of life doesn't require exotic conditions or rare elements. Instead, it emerges naturally from the most common molecules in the universe when they're given the right environment and enough time to experiment. Carbon, hydrogen, oxygen, nitrogen, elements abundant in early Earth's oceans, can combine in millions of different ways, and some of those combinations have surprising properties. Consider what happens when carbon atoms begin linking together into chains. Each carbon atom can form bonds with up to 4 other atoms, creating a framework that can grow in any direction. Add hydrogen atoms to stabilize the structure, and you get hydrocarbons, simple molecules that can serve as both building blocks and energy storage devices. These were among the first organic molecules to form in significant quantities in Earth's primordial seas. But carbon chains were just the beginning. When nitrogen and oxygen joined the molecular dance, the possibilities exploded. Amino acids, molecules that would eventually become the building blocks of proteins, began forming spontaneously in the warm water. These weren't just random assemblages of atoms. They were molecules with specific shapes, specific properties, specific behaviors that made them useful for building even more complex structures. The key insight from modern research is that these early organic molecules weren't just accumulating randomly, they were beginning to influence each other's formation and behavior. Some amino acids, when they clumped together, created environments that made it easier for other amino acids to form. Some carbon chains, when they reached a certain length, began to fold into shapes that could trap other molecules and concentrate them in specific locations. Dr. Maria Santos, studying prebiotic chemistry at the Institute for Advanced Molecular Studies, describes it this way: what we're seeing is the emergence of molecular neighborhoods. Certain molecules attract certain other molecules, creating clusters of complementary chemistry. It's like a city forming organically with different districts specializing in different types of chemical activity. These molecular neighborhoods were crucial for the next phase of chemical evolution. In the dilute waters of early oceans, most molecules were too far apart to interact regularly. But within these concentrated clusters, molecules could bump into each other thousands of times more frequently, dramatically increasing the chances of productive encounters. And productive encounters were exactly what began happening. Simple. Amino acids started linking together into short chains called peptides. These peptides had properties that individual amino acids lacked. They could fold into specific shapes. They could bind to particular molecules, and most importantly, some of them could catalyze chemical reactions. At the same time, another type of molecule was beginning its own evolutionary experiment. Nucleotides, compounds containing nitrogen, phosphorus, and sugar, were forming in the warm water and discovering their own remarkable property. They could line up in long chains, creating information-storing molecules that would eventually become RNA and DNA, but perhaps the most significant development was the emergence of molecules that could influence their own reproduction. Some of the early peptides had the ability to help amino acids link together more efficiently, essentially catalyzing their own formation. Some of the early nucleotide chains could serve as templates, guiding the formation of complementary chains that carried the same information. This was the beginning of molecular self-organization, chemistry that could perpetuate and improve itself. For the first time in the universe's 10 billion-year history, matter was learning to make copies of itself, to preserve information across generations, to evolve through trial and error toward greater complexity and efficiency. The process was still primitive, still prone to frequent failures and random errors. Most of these early experiments in self-organization fell apart quickly, their molecular structures too fragile to persist in the harsh conditions of primordial oceans. But the few that succeeded had a crucial advantage. They could multiply, creating more copies of successful designs, while failed experiments simply disappeared. This was natural selection at the molecular level, operating billions of years before the first living cell. Molecules that were better at self-replication became more common. Molecules that were better at catalyzing useful reactions found themselves in higher demand. Molecules that were better at working together in teams began to dominate the chemical landscape. But the early oceans weren't just a passive stage for these molecular experiments. The environment itself was evolving, creating new challenges and new opportunities for chemical innovation. Tidal pools concentrated molecules during low tide, then dispersed them during high tide, creating cycles of intense interaction followed by selection pressure. Underwater volcanic vents provided steady sources of energy and raw materials. Temperature gradients created currents that mixed different chemical neighborhoods, allowing successful innovations to spread. By 3.6 billion years ago, the oceans had become a vast network of interconnected molecular laboratories, each running thousands of experiments simultaneously. Simple compounds were organized into complex systems. Information was being stored and transmitted. Energy was being harvested and distributed. The fundamental processes of life were emerging from the chaos of chemistry. Yet these systems were still missing something essential. They could copy themselves, they could catalyze reactions, they could store information, but they couldn't maintain their organization against the constant pressure of entropy. They were like fires that burned brightly for a while before flickering out, unable to sustain themselves indefinitely. What they needed was a way to create boundaries, to separate their internal chemistry from the chaos of the external environment. They needed to become compartmentalized, to create the first distinction between self and not self that would define all future life. They needed to discover the secret of cellular organization. The molecular dance was accelerating, becoming more sophisticated with each passing million years. The players were taking their positions for the next great transformation, the emergence of the first protocells, the first entities that could truly be called the ancestors of all life on Earth. In the molecular laboratories of Earth's ancient oceans, a revolution was quietly unfolding. What had begun as random chemical encounters was evolving into something unprecedented. Specialized molecules, each designed by countless trials and errors to perform specific tasks in the grand experiment of life. By 3.7 billion years ago, the seas had become a vast assembly line where the universe was manufacturing its most sophisticated creations, the molecular building blocks that would construct every living thing that would ever exist. In the molecular laboratories of Earth's ancient oceans, a revolution was quietly unfolding. What had begun as random chemical encounters was evolving into something unprecedented: specialized molecules, each designed by countless trials and errors to perform specific tasks in the grand experiment of life. By 3.7 billion years ago, the seas had become a vast assembly line where the universe was manufacturing its most sophisticated creations, the molecular building blocks that would construct every living thing that would ever exist. To witness this transformation, we must understand that we're not just observing chemistry anymore, we're watching the birth of function. Every protein in your body today, every strand of DNA, every lipid membrane that surrounds your cells can trace its ancestry back to these primordial molecular innovations. The building blocks being forged in Earth's first oceans would prove so fundamentally useful that life would continue using them, virtually unchanged, for the next 4 billion years. The story begins with amino acids, perhaps the most elegant molecular invention in the history of chemistry. These remarkable compounds consist of just a few atoms arranged in a deceptively simple pattern. A central carbon atom bonded to an amino group, an acid group, and a unique side chain that gives each amino acid its distinctive personality. What makes amino acids extraordinary is not their individual properties, but their ability to link together like beads on a string, forming chains that can fold into virtually any shape imaginable. Some amino acids are hydrophobic, repelling water and seeking to hide inside protein structures. Others are hydrophilic, reaching out to interact with the watery environment. Some carry positive charges, others negative charges, creating electrical attractions that help stabilize complex molecular architectures. In 1953, Stanley Miller and Harold Urey demonstrated that amino acids form spontaneously when the chemical ingredients of early Earth are subjected to electrical discharges simulating lightning. Their famous experiment produced not just 1 or 2 amino acids, but nearly a dozen different types, a molecular toolkit that emerged naturally from the chaos of primordial chemistry. But modern research has revealed something even more remarkable. The amino acids that formed in Earth's early oceans weren't just random molecules, they were the same 20 amino acids that life uses today. Out of hundreds of possible amino acid structures, chemistry somehow converged on this specific set, this particular molecular alphabet that would become the language of all proteins. Dr. Jennifer Walsh, studying prebiotic chemistry at Cambridge, explains the significance. It's as if chemistry was conducting a 200 million year audition, testing every possible amino acid design. The 20 that life ultimately chose weren't random selections. They were the winners, the molecules that proved most versatile, most stable, most useful for building complex structures. While amino acids were learning to build proteins, another family of molecules was developing an entirely different expertise: information storage. Nucleotides, the building blocks of RNA and DNA, were emerging from the same chemical soup, but with a radically different mission. Instead of folding into complex shapes, they specialized in linking together into long, linear chains that could encode and transmit information. Each nucleotide consists of 3 components: a phosphate group that provides the backbone, a sugar that gives structural stability, and a nitrogenous base that carries the actual information. There are only 4 different bases in RNA: adenine, guanine, cytosine, and uracil. But these 4 letters proved sufficient to encode the instructions for every living thing that would ever exist. The formation of nucleotides in early oceans required more complex chemistry than amino acid synthesis. Phosphorus had to be extracted from minerals and combined with organic compounds in precisely the right proportions. Sugars had to form stable ring structures that could support the weight of genetic information. The bases had to develop the ability to recognize and pair with complementary partners. Yet somehow, against enormous odds, all these requirements were met. Recent experiments have shown that nucleotides can form spontaneously in conditions that mimic early Earth's volcanic pools, where cycles of heating and cooling concentrate reactants and drive complex chemical reactions. The genetic code wasn't invented by life, it was discovered by chemistry, exploring its own possibilities. But perhaps the most crucial molecular innovation was also the simplest: lipids, the fatty molecules that would eventually form the membranes surrounding every living cell. Unlike amino acids and nucleotides, which are complex and highly structured, lipids are almost embarrassingly simple. They consist of little more than carbon and hydrogen atoms arranged in long chains with a water-loving head group attached to one end. This simplicity, however, conceals extraordinary versatility. When lipids encounter water, their dual nature, hydrophilic heads and hydrophobic tails, forces them to organize spontaneously into structures that separate water from oil. In the ancient oceans, this meant that lipids naturally formed bubbles, sheets, and membranes wherever they accumulated in sufficient concentration. Modern scientists studying lipid formation have made a startling discovery. These molecules don't just form membranes randomly. They actively select for combinations that create the most stable, most flexible, most permeable boundaries. It's as if chemistry was experimenting with different membrane recipes, testing thousands of combinations until it found the formulations that would prove most useful for containing and protecting cellular chemistry. The convergence of these three molecular families, proteins for structure and catalysis, nucleic acids for information, lipids for compartmentalization, represents one of the most remarkable collaborations in the history of chemistry. Each family specialized in tasks that the others couldn't perform, yet all three proved essential for the next phase of chemical evolution. By 3.6 billion years ago, Earth's oceans contained all the molecular ingredients necessary for life. Amino acids were linking into peptide chains that could catalyze reactions and provide structural support. Nucleotides were assembling into information-carrying polymers that could store and transmit instructions. Lipids were organizing into membranes that could create separated spaces where complex chemistry could unfold without interference. But having the ingredients is not the same as having life. These molecular building blocks still needed to learn to work together, to coordinate their activities, to create systems that could persist and reproduce in the face of constant chemical and physical challenges. They needed to discover the secrets of cellular organization. The stage was now set for one of the most extraordinary events in cosmic history: the assembly of these specialized molecules into the first protocells, the first entities that could maintain their organization, reproduce their structures, and evolve toward greater complexity. The building blocks of eternity were ready to become the foundations of life itself. What happened next would transform not just Earth, but our understanding of what's possible when chemistry discovers the power of cooperation. In systems of unimaginable complexity emerging from the elegant simplicity of molecular collaboration, the universe was about to cross the threshold from chemistry to biology, from matter to life, from possibility to reality. There is a moment in the history of life so fundamental, so transformative, that every living thing on Earth, from the smallest bacteria to the most complex organism, bears witness to its importance with every breath. It's the moment when chemistry learned to create boundaries, when molecules discovered the power of separation, when the first membranes formed around collections of organic compounds and created something unprecedented: the distinction between inside and outside. To understand the magnitude of this breakthrough, imagine trying to conduct a complex symphony orchestra in the middle of a crowded marketplace. The musicians are talented, the music is beautiful, but the chaos of the surrounding environment makes coordination impossible. Now imagine building walls around your orchestra. Suddenly the music becomes clear, the coordination becomes possible, and something beautiful emerges from what was previously just noise. This is exactly what happened when the first lipid membranes formed in Earth's ancient oceans. For hundreds of millions of years, the chemistry of life had been unfolding in the open water, where useful molecules were constantly diluted by the vast seas, where productive reactions were interrupted by random interference, where complex systems could never maintain their organization long enough to evolve toward greater sophistication. The solution came from molecules so simple they seem almost mundane. Fatty acids and other lipids that had been accumulating in tidal pools and shallow seas. These molecules possess a unique architecture, a water-loving head attached to a water-repelling tail that creates an irresistible urge to organize whenever they encounter water in sufficient concentration. Dr. David Deamer, one of the world's leading experts on membrane formation, describes what happens next. When lipids reach a critical concentration in water, they don't just dissolve randomly. They actively organize themselves into structures that minimize contact between their hydrophobic tails and the surrounding water. It's not just chemistry, it's architecture, and the architecture is dictated by the fundamental forces that govern molecular behavior. The process is remarkably elegant. Individual lipid molecules begin to align with their heads facing outward toward the water, and their tails facing inward toward each other. As more molecules join this arrangement, they form first a single layer, then a double layer, a bilayer membrane that creates a barrier between two aqueous environments while remaining flexible and dynamic. But here's where the story becomes truly extraordinary. These membranes don't just form flat sheets. In the three-dimensional environment of ancient oceans, they naturally curve back on themselves, forming closed spheres called vesicles. Suddenly, for the first time in Earth's history, there were discrete volumes of water separated from the larger ocean, microscopic containers where chemistry could unfold without interference. These first protocells were nothing like modern cells. They had no complex internal machinery, no genetic systems, no elaborate metabolic networks. They were simply hollow spheres of membrane floating in primordial seas, occasionally incorporating dissolved organic molecules from their surroundings. Yet they represented one of the most significant innovations in the history of chemistry, the creation of inside and outside. The implications were staggering. Inside these membrane-bound spaces, the concentration of organic molecules could build to levels thousands of times higher than in the surrounding ocean. Chemical reactions that were statistically impossible in the dilute seas became probable, even inevitable, in the concentrated environment of protocell interiors. Modern experiments have revealed just how dramatically membranes change the rules of chemistry. When researchers create artificial vesicles and introduce the same organic molecules that existed in early oceans, complex reactions begin spontaneously that never occur in open solution. Amino acids link into peptides more readily. Nucleotides assemble into longer chains. Catalytic molecules become dramatically more effective at promoting the reactions they facilitate. But membranes did more than just concentrate reactants. They also created the first primitive metabolism. The lipid boundaries weren't perfectly sealed. They were selectively permeable, allowing some molecules to pass through while blocking others. Small, useful molecules like amino acids and nucleotides could enter the protocells, while larger products of chemical reactions were retained inside. This created the first chemical gradients across biological membranes, the first primitive energy systems that could drive complex reactions. The protocells became molecular refineries, taking in raw materials from their environment and concentrating useful products in their interiors. Even more remarkably, these early membranes displayed a primitive form of growth and reproduction. As the chemical reactions inside protocells produced more lipid molecules, the membranes expanded. When they reached a critical size, physical forces caused them to divide into two smaller vesicles, each carrying a sample of the parent's internal chemistry. It wasn't true biological reproduction. There was no genetic control, no precise copying of internal systems. But it was a form of heredity nonetheless, a way for successful chemical combinations to multiply while unsuccessful ones disappeared. natural selection was beginning to operate at the cellular level. Dr. Sheriff Mansi, studying protocell evolution at the University of Trento, has made a remarkable discovery about these early membrane systems. They're not just passive containers. The membranes themselves participate in the chemistry happening inside. They can catalyze certain reactions, stabilize specific molecules, and even influence which chemical pathways are favored. The boundary between container and content starts to blur. This active participation of membranes in cellular chemistry helps explain one of the great puzzles of early evolution: how complex biochemical systems could emerge before sophisticated genetic control systems existed. The membranes themselves were providing a form of chemical information, guiding the development of internal chemistry through their selective permeability and catalytic properties. By 3.5 billion years ago, the oceans were populated by countless millions of these protocells, each one a unique experiment in contained chemistry. Some developed more efficient membranes that better retained useful molecules. Others evolved internal chemistry that produced membrane components more rapidly. A few discovered ways to capture energy from their environment and use it to drive chemical reactions that wouldn't occur spontaneously. Competition between protocells was driving rapid innovation. Those with the most effective membranes grew faster and divided more frequently. Those with the most productive internal chemistry accumulated more resources and survived longer. The stage was set for the next great breakthrough: the development of systems that could store and transmit information about successful chemical combinations. But even as we marvel at the sophistication that was beginning to emerge, we must remember that these protocells were still incredibly primitive compared to modern cells. They had no DNA, no proteins in the modern sense, no elaborate metabolic pathways. What they had was something equally precious: enclosed spaces where chemistry could experiment with complexity without constant interference from the chaotic environment outside. The membrane miracle had transformed Earth's oceans from a dilute chemical soup into a vast array of microscopic laboratories, each one testing different approaches to organized chemistry. The most successful innovations would be preserved and passed on to future generations. The failures would dissolve back into the sea, their components recycled for new experiments. Life hadn't yet learned to live, but it had learned to concentrate, to organize, to maintain boundaries against entropy. The first cells had formed, and with them, the foundation for every biological innovation that would follow. Inside the membrane-bound protocells floating in Earth's ancient seas, something revolutionary was stirring. Among the countless molecular experiments unfolding in these microscopic laboratories, one family of molecules was developing capabilities that would change the rules of chemistry forever. RNA, ribonucleic acid, was learning to do something unprecedented in the universe's history. It was learning to think, to remember, and to pass its thoughts to the next generation. To understand the magnitude of this breakthrough, we must recognize that RNA solved two of the greatest challenges facing early life simultaneously. Until this point, chemistry had produced molecules that could either store information or catalyze reactions, but never both. Proteins were excellent catalysts, but couldn't preserve information about how to make more proteins. DNA-like molecules could store information, but were helpless to act on that information. RNA changed everything by becoming the first molecule that could serve as both gene and enzyme, both library and librarian. This dual capability emerged from RNA's unique structure. Unlike the double helix of DNA, which is locked into a stable but relatively inflexible form, RNA exists as a single strand that can fold and twist into an almost infinite variety of three-dimensional shapes. Some of these shapes are perfect for storing information: long, linear sequences where each nucleotide position can encode instructions. Others are ideal for catalyzing reactions, complex structures with precisely positioned atoms that can grab other molecules and help them transform. Dr. Thomas Seck, whose Nobel Prize-winning research first demonstrated RNA's catalytic abilities, describes the discovery that changed our understanding of early life. When we realized that RNA could cut and splice itself, could catalyze its own replication, could regulate gene expression, we suddenly understood that life didn't need to wait for proteins to evolve. RNA could bootstrap the entire process, creating systems of increasing complexity from surprisingly simple beginnings. In laboratories around the world today, scientists are recreating the conditions of the RNA world, that hypothetical period between 3.8 and 3.5 billion years ago, when RNA molecules dominated the chemistry of life. What they're discovering is that RNA's capabilities extend far beyond what anyone imagined just a few decades ago. Modern RNA molecules can build themselves from simple nucleotide building blocks. They can make copies of other RNA molecules. They can regulate their own activity by binding to specific target sequences. They can even evolve, changing their structure over successive generations to become more efficient at whatever task they're performing. In essence, RNA molecules can display all the fundamental properties of life: growth, reproduction, heredity, and evolution. But for RNA to establish its ancient kingdom, it first had to emerge from the chemical chaos of protocell interiors. This required a series of molecular innovations that pushed chemistry to its limits. Nucleotides had to link together into longer chains without the help of sophisticated enzymes. These chains had to develop the ability to fold into stable three-dimensional structures. And, most remarkably, some of these structures had to acquire the ability to catalyze the formation of more RNA molecules. The breakthrough came when certain RNA sequences discovered they could act as ribozymes, RNA molecules with enzyme-like properties. The first ribozymes were probably simple structures that could help nucleotides link together more efficiently, essentially catalyzing their own growth. But once this basic capability existed, evolution could begin optimizing it, creating RNA molecules that were increasingly sophisticated at manipulating their chemical environment. Recent experiments have shown that ribozymes can evolve remarkably quickly when subjected to selective pressure. Starting with random RNA sequences, researchers can generate ribozymes with specific catalytic abilities in just a few dozen generations of evolution. If this can happen in modern laboratories over weeks or months, imagine what could be achieved in ancient oceans over millions of years. But RNA's most revolutionary innovation was the development of self-replication. Around 3.6 billion years ago, some RNA molecules acquired the ability to make copies of themselves, creating the first true hereditary systems. This wasn't the precise, error-free replication we see in modern cells, but it was good enough to allow successful molecular designs to multiply while unsuccessful ones disappeared. Dr. Gerald Joyce, who has spent decades studying RNA evolution, explains the significance. Once RNA could replicate itself, even imperfectly, you had the fundamental requirements for Darwinian evolution. Variation occurred through replication, errors. Selection operated as some RNA variants proved more successful at surviving and reproducing. Over time, this process could generate increasing complexity and sophistication. The RNA world wasn't a gentle, gradual emergence of life. It was an explosion of molecular innovation driven by fierce competition between different RNA species. Those that could replicate faster dominated the available resources. Those that could catalyze useful reactions gained advantages in gathering nucleotide building blocks. Those that could resist degradation survived longer in the harsh chemical environment of early cells. Within this competitive environment, RNA molecules began developing increasingly sophisticated capabilities. Some specialized in information storage, becoming the first primitive genomes. Others focused on catalytic functions, becoming the first metabolic enzymes. Still others discovered regulatory roles, controlling when and where different chemical reactions occurred. Most remarkably, RNA molecules began working together, forming networks where different molecules performed complementary functions. Some RNA species became specialists at gathering raw materials. Others focused on energy production. Still others handled waste removal or defense against molecular parasites. The first ecosystems were emerging at the molecular level, but the RNA world faced a fundamental limitation. RNA molecules are inherently unstable compared to modern biological molecules. They're vulnerable to chemical degradation, prone to structural damage, and limited in the range of functions they can perform compared to proteins. The RNA kingdom was remarkably sophisticated, but it was also fragile. The solution came through one of evolution's most elegant innovations, the development of protein synthesis. Some RNA molecules discovered they could serve as templates for building protein molecules, which were far more stable and versatile than RNA itself. Initially, this was probably just another chemical reaction that some ribozymes happened to catalyze, but it would prove to be the innovation that transformed life itself. By learning to make proteins, RNA gained access to a vast, new range of chemical capabilities. Proteins could catalyze reactions that RNA couldn't perform. They could build structural components that were far more durable than RNA molecules. They could create transport systems, energy production systems, and defense systems that were impossible with RNA alone. Yet even as proteins began taking over many of RNA's functions, the ancient kingdom left an indelible mark on all future life. The genetic code, the system that translates RNA information into protein structures, remains virtually unchanged after 3.5 billion years. The ribosome, the cellular machine that builds proteins, is fundamentally an RNA enzyme surrounded by protein accessories. Transfer RNAs still carry amino acids to the sites where proteins are assembled. Most importantly, RNA retained its original role as the master information processor. Modern DNA may store genetic information more stably than RNA, but RNA still serves as the messenger that carries genetic instructions from storage to implementation. Every gene in your body is transcribed into RNA before its information can be used to build proteins. The RNA world taught chemistry its most profound lesson. Information is power. Molecules that could store, process, and transmit information about successful chemical strategies gained enormous advantages over those that couldn't. This principle would become the driving force behind all subsequent evolution, leading eventually to DNA-based genomes, complex metabolic networks, and ultimately to brains capable of processing information about the external world. As we prepare to witness the next great transformation, the integration of replication, metabolism, and compartmentalization into the first true living cells, we must remember that RNA's ancient kingdom provided the template for all future biological organization. The information processing systems pioneered by RNA molecules 3.6 billion years ago continue to operate in every cell of your body, preserving and transmitting the molecular wisdom accumulated over billions of years of evolution. There is a moment in the story of life that represents the most profound threshold in cosmic history, the moment when molecules learn to make perfect copies of themselves. Not approximate copies, not rough sketches, but precise duplicates that could preserve information across countless generations without loss or degradation. This breakthrough, occurring roughly 3.5 billion years ago, transformed chemistry into biology and created the mechanism through which the universe would eventually learn to understand itself. To appreciate the magnitude of this achievement, consider the challenge these early molecular systems faced. In the chaotic environment of protocells, where temperatures fluctuated wildly and chemical conditions changed by the minute, creating an exact molecular copy seemed virtually impossible. It would be like trying to reproduce a complex symphony. While standing in the middle of an earthquake, the precision required defies comprehension. Yet somehow, through billions of molecular experiments and countless evolutionary iterations, early RNA systems discovered the secret of high-fidelity replication. The breakthrough came not through a single innovation, but through a series of interlocking discoveries that transformed error-prone copying into a reliable system for preserving and transmitting information. The first step was the development of template-based copying. Early RNA molecules discovered that they could serve as patterns for building complementary strands, where each nucleotide in the original sequence specified exactly which nucleotide should be placed in the corresponding position of the copy. This wasn't entirely new. RNA had been able to do rough template copying for millions of years, but the early versions were plagued by errors, with wrong nucleotides being incorporated roughly once every 100 positions. For simple, short RNA molecules, this error rate was survivable. But as RNA systems grew more complex and began storing more sophisticated information, copying errors became catastrophic. A single wrong nucleotide in a critical position could destroy a ribozyme's catalytic activity or eliminate an RNA molecule's ability to regulate other molecular processes. Dr. Andrew Ellington, studying the evolution of replication systems at the University of Texas, describes the challenge. Early life faced what we call an error catastrophe. If your replication system makes too many mistakes, you lose the information faster than you can preserve it. The system collapses back into random chemistry. To cross the threshold into stable heredity, these early molecular systems had to achieve copying fidelities that seemed almost impossibly precise. The solution came through the evolution of proofreading mechanisms, molecular systems that could recognize when mistakes had been made during copying and correct them before they became permanently incorporated. This required RNA molecules to develop a kind of molecular perfectionism, the ability to distinguish between correct and incorrect copies with extraordinary precision. Modern research has revealed how this proofreading evolved. Initially, some RNA molecules developed the ability to recognize and remove incorrectly paired nucleotides during the copying process itself. Later, more sophisticated systems emerged that could scan completed copies and identify errors that had escaped detection during synthesis. But achieving high copying fidelity required more than just error correction. It demanded fundamental innovations in the mechanics of replication itself. Early RNA systems had to develop processivity, the ability to complete long copying reactions without dissociating from their templates. They needed to evolve directional copying mechanisms that proceeded systematically from one end of a molecule to the other. Most importantly, they had to discover ways to ensure that copying proceeded at optimal speeds, fast enough to outcompete rival systems, but slow enough to maintain accuracy. The evolutionary pressure driving these innovations was intense. In the competitive environment of protocells, molecular systems that could replicate more accurately gained enormous advantages. They could preserve useful innovations across generations, while their error-prone competitors gradually lost their functional capabilities through accumulated mutations. By 3.4 billion years ago, some RNA-based systems had achieved copying fidelities approaching those of modern biological systems. Error rates of less than one mistake per 1,000 nucleotides copied. This level of precision was sufficient to maintain complex genetic information across hundreds of generations, creating stable molecular lineages that could accumulate improvements over time. But high-fidelity replication created a new challenge: how to balance the preservation of successful molecular designs with the generation of variations that could lead to future improvements. Pure copying accuracy would create molecular systems that were perfectly stable but incapable of evolutionary innovation. The solution was the development of controlled mutation systems, mechanisms that could introduce occasional, deliberate changes into copied sequences. Dr. Gerald Joyce, whose laboratory has created self-replicating RNA systems that can evolve in real time explains this balance. Evolution requires both preservation and innovation. The most successful early replication systems weren't those with perfect copying fidelity, but those that achieved optimal mutation rates, high enough to generate useful variations, low enough to preserve successful innovations. This controlled balance between stability and change became the foundation for all subsequent evolution. RNA systems that achieved optimal mutation rates could explore new molecular possibilities while maintaining their core functions. They became the first true organisms capable of both preserving their essential characteristics and adapting to changing environmental conditions. The implications extended far beyond individual molecular systems. High-fidelity replication enabled the first genetic cooperation where different RNA molecules could work together because each could reliably produce the molecular partners it depended on. This led to the emergence of the first molecular ecosystems, where specialized RNA species performed complementary functions in stable, long-term associations. But perhaps the most profound consequence of reliable replication was the emergence of molecular memory. For the first time in the universe's history, information about successful chemical strategies could be preserved indefinitely, accumulating wisdom across geological timescales. Each successful innovation could serve as the foundation for future discoveries, creating an exponential growth in molecular sophistication. Modern molecular biologists studying this period have made a remarkable discovery: the replication machinery that evolved during this ancient revolution still operates in every living cell today. The fundamental mechanisms of DNA replication, template-based copying, proofreading, directional synthesis, all trace their ancestry back to these early RNA systems. Even more remarkably, the molecular machines that perform replication in modern cells retain clear signatures of their RNA origins. The DNA polymerases that copy genetic information are protein enzymes, but they're assisted by RNA primers and RNA cofactors. The replication machinery is fundamentally RNA-based technology that has been enhanced and optimized by protein components. By 3.3 billion years ago, the replication revolution had transformed Earth's oceans from a collection of competing molecular systems into networks of cooperating genetic lineages. The first stable hereditary systems had emerged, creating molecular dynasties that could persist for millions of years while continuously innovating and improving their capabilities. The stage was set for the next great breakthrough: the integration of reliable replication with sophisticated metabolism, creating molecular systems that could not only copy themselves accurately, but also harness energy from their environment to power growth, reproduction, and evolution. The replication revolution had solved one of the fundamental challenges of life: how to preserve and transmit complex information across generations. But possessing stable genetic systems was only half the battle. These early organisms also needed to develop the metabolic machinery that could capture energy from their environment and use it to fuel the expensive processes of growth and reproduction. Inducting the protected spaces of early protocells where reliable replication had begun preserving molecular wisdom across generations, a new challenge was emerging. These increasingly sophisticated systems required enormous amounts of energy to fuel their growth, reproduction, and maintenance. Simply storing information was no longer enough. Life needed to learn how to eat, how to breathe, how to transform the raw materials of ancient oceans into the complex biochemical machinery of living systems. The solution came through the evolution of metabolism, networks of chemical reactions that could capture energy from the environment and channel it into useful work. But this wasn't just about finding fuel, it was about developing sophisticated energy management systems that could operate continuously, efficiently, and with the precision required to support life's growing complexity. The first metabolic innovations emerged from the basic chemistry of ancient oceans themselves. The mineral-rich waters surrounding protocells contained abundant sources of chemical energy, dissolved organic compounds from volcanic vents, metal ions that could participate in electron transfer reactions, and simple molecules like hydrogen sulfide that could be oxidized to release energy. Dr. William Martin, studying the metabolic origins of life at Heinrich Heine University, describes these early energy systems. The first metabolism wasn't invented by life, it was discovered. The chemical reactions that power modern cells are essentially the same. Reactions that occurred spontaneously at hydrothermal vents billions of years ago. Life learned to harness processes that were already happening in the environment. The breakthrough came when RNA-based systems developed the ability to catalyze and control these energy-releasing reactions. Instead of letting chemical energy dissipate randomly as heat, early ribozymes learned to capture this energy and store it in molecular batteries, compounds that could hold energy until it was needed for cellular processes. The most important of these energy storage molecules was probably an ancient ancestor of ATP, adenosine triphosphate, the universal energy currency of modern cells. This remarkable molecule could absorb energy from metabolic reactions and then release it on demand to power everything from replication to membrane maintenance to the synthesis of complex biomolecules. But early metabolism faced a fundamental challenge: efficiency. The first metabolic pathways were crude, wasteful affairs that lost most of their energy as heat rather than capturing it for useful work. Evolution needed to optimize these systems, creating metabolic networks that could extract maximum energy from available resources while minimizing waste. The solution came through the development of metabolic pathways, sequences of linked reactions, where the products of one reaction become the inputs for the next. By chaining reactions together, early cells could extract far more energy from their fuel molecules than any single reaction could provide. Modern research has revealed that these ancient metabolic pathways show remarkable similarity to the central energy processing systems used by all life today. The citric acid cycle, which extracts energy from organic molecules in modern cells, appears to be a direct descendant of metabolic networks that first evolved in protocells billions of years ago. But metabolism did more than just provide energy. It created the first truly autonomous systems, entities that could maintain themselves independently of their environment. By developing internal energy production, early cells became less dependent on the random availability of external energy sources. They could regulate their own activity, control their own growth, and maintain complex internal chemistry even when environmental conditions were unfavorable. By 3.5 billion years ago, all the essential components of life had been discovered and refined through hundreds of millions of years of molecular evolution. Reliable replication systems could preserve and transmit complex information. Sophisticated metabolic networks could harvest and manage energy. Flexible membrane boundaries could maintain cellular organization while allowing controlled exchange with the environment. The stage was set for the most remarkable integration in the history of chemistry. What happened next was nothing short of miraculous. These three fundamental systems learned to work together as a unified whole, creating the first entities that could truly be called alive. This wasn't just cooperation, it was the emergence of a new kind of organization where the whole became greater than the sum of its parts. The integration required exquisite coordination. Replication systems needed energy from metabolism to power the synthesis of new genetic material. Metabolic networks needed information from genetic systems to produce the right enzymes at the right times. Membrane systems needed products from both replication and metabolism to maintain their structure and regulate their permeability. Modern systems biologists studying this integration have discovered that it required the evolution of sophisticated regulatory networks, molecular control systems, that could coordinate the activity of different cellular processes. These early regulatory circuits represented some of the first examples of biological information processing, where cells could sense their internal state and adjust their behavior accordingly. Dr. Urs Sathmari, a leading expert in early evolution at Eötvös-Loránd University, explains the significance. The Great Assembly wasn't just about combining existing systems, it was about creating entirely new properties that emerged from their integration. For the first time, you had entities that could grow, reproduce, evolve, and maintain themselves as autonomous units. This was the birth of true organisms. The first integrated cells were still incredibly simple compared to modern life forms. They had no nuclei, no complex organelles, no sophisticated sensory systems, but they possessed the fundamental characteristics that define life. They could maintain their organization against entropy, reproduce their structures with high fidelity, and evolve in response to environmental challenges. These early organisms immediately began diversifying, exploring different strategies for survival and reproduction. Some specialized in extracting energy from organic compounds dissolved in seawater. Others learned to harvest energy from chemical reactions involving dissolved minerals. A few pioneered entirely new approaches, developing primitive forms of photosynthesis that could capture energy directly from sunlight. The diversity explosion was driven by the same evolutionary forces that had shaped molecular systems, but now operating at a higher level of organization. Cells that were more efficient at energy production could grow faster and reproduce more frequently. Those that were better at avoiding damage could survive longer and accumulate more improvements over time. Most importantly, the integration of replication, metabolism, and compartmentalization created positive feedback loops that accelerated evolutionary innovation. Better metabolic systems provided more energy for replication, leading to more accurate copying and faster evolution. Improved replication systems could preserve more sophisticated metabolic innovations, leading to greater energy efficiency. Enhanced membrane systems could maintain more complex internal chemistry, enabling both better metabolism and more reliable replication. The story we've been telling, this epic journey from lifeless chemistry to living cells, might seem like pure speculation, a scientific fairy tale constructed from theoretical possibilities rather than hard evidence. But scattered across our planet, hidden in some of the most ancient rocks on Earth, lies proof that this extraordinary transformation really happened. The evidence comes in many forms, each piece of the puzzle contributing to our understanding of life's earliest chapters. Some of the most spectacular proof can be found in formations called stromatolites, layered rock structures created by ancient microbial communities. These fossilized bacterial mats, some dating back 3.5 billion years, provide direct visual evidence of early life's existence. But stromatolites tell us more than just that early life existed, they reveal how it lived. The layered structures show seasonal growth patterns, evidence that early microbial communities were already sophisticated enough to respond to environmental cycles. The chemical composition of these ancient deposits reveals what these early organisms ate, how they processed energy, and even hints about the atmospheric conditions they lived in. Dr. Abigail Allwood, whose research at NASA's Jet Propulsion Laboratory focuses on the earliest signs of life, describes what stromatolites reveal. These aren't just random bacterial deposits. They show evidence of coordinated community behavior with different types of microorganisms occupying different layers and performing complementary functions. We're seeing ecosystems that were already sophisticated 3.5 billion years ago. Even more compelling evidence comes from chemical signatures preserved in ancient rocks. When early life processed organic compounds or participated in metabolic reactions, it left characteristic isotopic fingerprints, slight variations in the ratios of different atomic forms that can be detected billions of years later. These chemical fossils tell remarkable stories. Carbon isotope ratios in 3.8 billion-year-old rocks from Greenland show patterns that are virtually identical to those produced by modern biological processes. Sulfur isotopes from the same period reveal evidence of metabolic pathways that still operate in bacteria today. The chemistry of life has remained remarkably consistent across nearly 4 billion years of evolution. But perhaps the most profound evidence comes from life itself. Every organism on Earth, from the simplest bacteria to the most complex plants and animals, shares the same fundamental biochemistry. We all use the same genetic code, the same basic metabolic pathways, the same membrane structures. This unity of biochemistry across all life forms points to a single origin, a common ancestor from which every living thing descended. Modern molecular biologists have used this shared biochemistry to reconstruct the characteristics of LUCA, the last universal common ancestor, the organism that gave rise to all current life on Earth. LUCA probably lived around 3.5 billion years ago and already possessed sophisticated systems for replication, metabolism, and cellular organization. It was a fully integrated living system, the culmination of hundreds of millions of years of chemical evolution. The evidence also reveals that early life was far more diverse than we once imagined. Ancient rocks contain chemical signatures from organisms that used metabolic pathways completely different from anything alive today. Some appear to have been specialized for extreme environments, superhot volcanic vents, highly acidic pools, or regions with crushing pressure. Early life was already exploring every possible ecological niche, pushing the boundaries of what biology could achieve. Just when early life had achieved a stable balance between replication, metabolism, and cellular organization, evolution stumbled upon an innovation so powerful, so transformative, that it nearly destroyed the very life that created it. Around 2.4 billion years ago, some microorganisms developed a revolutionary form of metabolism that would change not just the oceans, but the entire planet: oxygenic photosynthesis. The innovation seemed innocent enough at first. A group of bacteria, called cyanobacteria, learned to harvest energy directly from sunlight using water as an electron donor. This was incredibly efficient. Sunlight was abundant and free, and water was everywhere in the ancient oceans. These photosynthetic bacteria could grow and reproduce faster than any organisms that had existed before. But there was a deadly side effect: oxygen. For every molecule of carbon dioxide that cyanobacteria converted into organic compounds, they released a molecule of oxygen gas into the water and atmosphere. To modern life, oxygen seems essential and benign, but to the organisms of 2.4 billion years ago, it was a toxic pollutant of unimaginable destructiveness. Oxygen is chemically aggressive. It reacts readily with organic molecules, breaking them down and destroying their function. The early atmosphere and oceans contained virtually no free oxygen because it would immediately react with dissolved iron, organic compounds, and other reducing materials. Life had evolved in this oxygen-free environment for over 1 billion years, and its biochemistry was completely unprepared for oxidative stress. Dr. Tim Lenton, studying atmospheric evolution at the University of Exeter, describes the crisis. The Great Oxidation Event was probably the most severe environmental catastrophe in Earth's history. It was a mass extinction caused not by an asteroid impact or volcanic eruption, but by life itself. The waste product of photosynthesis was literally poisoning the biosphere. As cyanobacteria spread across the ancient oceans, oxygen concentrations began to rise dramatically. Most of the existing microbial life simply couldn't survive in this increasingly toxic environment. Species that had dominated the Earth for over 1 billion years were driven to extinction or forced to retreat to oxygen-free refuges in deep ocean sediments and other isolated environments. The crisis lasted for hundreds of millions of years. A period geologists call the Great Oxidation Event. Ocean chemistry was completely transformed as dissolved iron reacted with oxygen to form massive banded iron formations, geological structures that still exist today as testament to this ancient catastrophe. The atmosphere itself was revolutionized as oxygen levels rose from virtually zero to significant concentrations. But crisis also created opportunity. The few organisms that survived the oxygen catastrophe were those that managed to evolve biochemical defenses against oxidative damage. Some developed antioxidant systems that could neutralize harmful oxygen radicals. Others learned to use protective compounds that could shield their cellular machinery from oxygen damage. Most remarkably, some organisms discovered that oxygen, despite its toxicity, could be harnessed as an incredibly powerful energy source. Aerobic respiration, the process of using oxygen to extract energy from organic molecules, yields far more energy than any anaerobic metabolic pathway. Organisms that mastered this dangerous but profitable chemistry gained enormous advantages over their competitors. The oxygen catastrophe fundamentally changed the rules of evolution. Suddenly, there was selection pressure for organisms that could not only tolerate oxygen but actually benefit from it. This drove the evolution of increasingly sophisticated cellular machinery, including the first primitive versions of the organelles that would eventually become mitochondria, the powerhouses of modern cells. By 2 billion years ago, Earth had been transformed into an oxygenated world where aerobic metabolism dominated. The crisis had passed, but its effects would be permanent. The oxygen-rich atmosphere created conditions that would eventually enable the evolution of complex multicellular life, while the organisms that had survived the catastrophe became the ancestors of all modern aerobic life. The Great Oxidation event taught us one of evolution's most important lessons. Innovation always comes with risk. The same creativity that drives biological progress can also create existential threats. But life's response to the oxygen catastrophe also demonstrated evolution's remarkable resilience and adaptability. Even the most severe environmental crisis can become an opportunity for those organisms capable of evolutionary innovation. Our next chapter explores how the survivors of the oxygen catastrophe used their new energy-rich chemistry to evolve toward greater complexity, leading eventually to the emergence of eukaryotic cells and the first tentative steps toward multicellular organization. The oxygen catastrophe had transformed Earth into a fundamentally different planet, but the survivors of that great crisis carried within them the seeds of even greater transformations. The energy-rich chemistry made possible by aerobic respiration was about to fuel the most remarkable leap in biological complexity since life first emerged, the evolution of eukaryotic cells and the birth of multicellular life. For nearly 1.5 billion years after the oxygen crisis, life remained relatively simple. The bacterial cells that dominated the post-catastrophe world were sophisticated in their biochemistry but limited in their structural complexity. They lacked internal compartments, organized genomes, or the elaborate cellular machinery that characterizes modern plants, animals, and fungi. Evolution seemed to have reached a stable plateau. Then around 2 billion years ago, something extraordinary happened. Some bacterial cells began incorporating other bacteria as permanent internal residents. This wasn't predation or parasitism. It was the beginning of the most successful partnership in the history of life. The larger cells provided protection and resources, while the smaller cells contributed specialized functions, particularly the ability to process oxygen safely and efficiently. Dr. Lynn Margulis revolutionized our understanding of this process with her endosymbiotic theory, which explains how complex cells evolved through the merger of simpler organisms. Her research revealed that the powerhouses of modern cells, mitochondria, are actually the evolutionary descendants of ancient bacteria that took up residence inside other cells billions of years ago. The evidence for this bacterial origin of cellular organelles is overwhelming. Mitochondria have their own DNA, separate from the cell's nuclear genome. They reproduce independently by dividing, just like bacteria. Their ribosomes and metabolic pathways more closely resemble bacterial systems than those of their host cells. Most remarkably, the DNA sequences of mitochondria clearly show their relationship to specific groups of modern bacteria. But mitochondria were just the beginning. Plants acquired a second type of bacterial partner, chloroplasts, the descendants of ancient cyanobacteria that brought the power of photosynthesis inside eukaryotic cells. This dual endosymbiosis created organisms that could both produce their own food through photosynthesis and process it efficiently through aerobic respiration. Dr. Patrick Keeling, studying eukaryotic evolution at the University of British Columbia, explains the transformative impact. Endosymbiosis didn't just add new capabilities to cells, it multiplied their energy budget by orders of magnitude. A eukaryotic cell with mitochondria can produce 20 times more energy than a comparable bacterial cell. That energy surplus funded all the complexity that followed. The energy windfall from endosymbiosis enabled eukaryotic cells to evolve features that were impossible for bacteria to maintain. They developed nuclei to organize their expanding genomes. They created elaborate cytoskeletons that could change cell shape and enable movement. They evolved complex membrane systems that could compartmentalize different biochemical processes. Most importantly, the energy and structural complexity of eukaryotic cells made multicellularity possible. Individual cells could specialize for different functions because they were part of larger organisms that could support such specialization. Some cells could focus on gathering nutrients, others on reproduction, still others on protection or communication. The first multicellular organisms appeared around 1 billion years ago, simple colonies where individual cells remained largely independent but gained benefits from cooperation. These early experiments in multicellularity were tentative, easily reversible arrangements that probably evolved and dissolved countless times as conditions changed. But by 600 million years ago, something clicked. Multicellular organisms began, evolving true tissue-level organization, where cells became permanently specialized and interdependent. This was the foundation for everything that would follow. Every plant, every animal, every fungus that has ever lived traces its ancestry back to these early multicellular pioneers. The ocean chemistry that had enabled the first life was still playing a crucial role in these evolutionary innovations. The dissolved minerals, the pH balance, the temperature ranges, all the chemical parameters that had originally made life possible were now supporting increasingly complex biological processes. But perhaps the most remarkable aspect of this evolutionary journey is how it built upon the foundation laid by the first oceans. The same water molecules that had enabled the first chemical reactions were now flowing through the circulatory systems of multicellular organisms. The same dissolved ions that had facilitated early metabolism were now being used for nerve conduction and muscle contraction. Modern molecular biologists studying this period have discovered that many of the genetic and biochemical innovations that enabled multicellularity were actually present in much simpler organisms. They just weren't being used for complex organization. Evolution didn't invent new molecular tools for building complex life. It repurposed ancient mechanisms that had been refined over billions of years of cellular evolution. The transition from simple cells to complex organisms wasn't a single revolutionary event. It was a gradual climb up complexity's ladder, with each step building on the innovations that came before. Ocean chemistry had provided the foundation, endosymbiosis had supplied the energy, and time had allowed evolution to explore the vast space of biological possibilities. 4 billion years after chemistry first crossed the threshold into biology, in Earth's ancient oceans, scientists in laboratories around the world are attempting something that would have seemed impossible just a few decades ago. They're trying to recreate the origin of life itself. These modern laboratories have become time machines, allowing us to peer back into the molecular events that transformed our planet from a lifeless rock into a living world. The challenge is staggering in its complexity. Researchers must not only understand the chemical processes that led to life's emergence, but actually reproduce them under controlled conditions. They're essentially trying to compress hundreds of millions of years of molecular evolution into experiments that last weeks or months, guided by theoretical understanding and informed by the fossil record of ancient chemistry. Dr. Jack Szostak, whose Nobel Prize-winning research focuses on the origins of cellular life, describes the ambitious scope of this research. We're not just trying to understand how life began, we're trying to build it from scratch. We want to create self-replicating systems that can evolve, that can develop metabolism, that can cross the threshold from chemistry to biology right here in our laboratories. The experiments begin with the same raw materials that were available. In Earth's primordial oceans, simple organic molecules, dissolved minerals, water, and energy sources that can drive chemical reactions. But creating life isn't just about mixing ingredients. It requires understanding the specific conditions and sequences of events that can guide chemistry toward biology. One of the most successful approaches involves creating artificial protocells, membrane-bound vesicles that can encapsulate simple chemical systems and allow them to evolve in controlled environments. These laboratory protocells can grow, divide, and even undergo a primitive form of natural selection as different vesicle populations compete for limited resources. Recent breakthroughs have been remarkable. Researchers have created RNA molecules that can replicate themselves with increasing accuracy over successive generations. They've built metabolic networks that can sustain themselves on simple chemical inputs. They've developed membrane systems that can grow and divide while maintaining their internal chemistry. Dr. Sheriff Mansi, leading protocell research at the University of Trento, has achieved one of the most significant milestones in origin of life. Studies creating protocells that can undergo Darwinian evolution. We start with a population of vesicles that are all slightly different from each other. We subject them to selective pressure, and we watch as the most successful variants become more common over time. We're witnessing evolution happening in real time, but these experiments reveal just how improbable life's origin really was. Even with careful design, optimal conditions, and constant supervision, creating self-sustaining living systems remains extraordinarily difficult. The researchers must balance dozens of variables simultaneously: temperature, pH, chemical concentrations, energy inputs, to create conditions where chemistry can cross the threshold into biology. The implications extend far beyond academic curiosity. Understanding how life begins has practical applications for biotechnology, medicine, and astrobiology. If scientists can master the principles of creating life from scratch, they might be able to design organisms with specific capabilities: bacteria that can clean up environmental pollution, cells that can produce important medicines, or biological systems that can survive in extreme environments. Perhaps most importantly, these experiments are providing insights into the fundamental question that drives all origin of life research. Is life an inevitable consequence of chemistry under the right conditions, or was it an incredibly unlikely accident that happened to occur on Earth? The emerging evidence suggests that life might be more probable than we once thought. When researchers create the right chemical conditions, self-organizing systems tend to emerge spontaneously. Complex molecules show a natural tendency to cooperate and form networks. Information-carrying systems develop the ability to evolve and improve themselves. Dr. Lee Cronin, developing new approaches to artificial life at the University of Glasgow, offers a provocative perspective. What we're discovering is that chemistry wants to become biology. Given the right conditions and enough time, the emergence of lifelike properties seems almost inevitable. The universe appears to have a built-in tendency toward increasing complexity and organization. But even as scientists make remarkable progress in recreating life's origin, they're also gaining deeper appreciation for the extraordinary chain of events that occurred in Earth's ancient oceans. Every successful experiment reveals new layers of complexity, new requirements that must be met, new improbabilities that somehow were overcome during life's actual emergence. As scientists work to recreate the origins of life in their laboratories, a parallel revolution is unfolding in space exploration. Robotic missions throughout our solar system are discovering that Earth's oceans, the cradles of life as we know it, may not be unique. Hidden beneath the icy surfaces of distant moons warmed by gravitational forces, we're only beginning to understand vast oceans may be harboring their own experiments in chemistry and biology. The story begins with Europa, Jupiter's ice-covered moon, where tidal forces from the giant planet's gravity continuously stretch and squeeze the rocky interior, generating heat that keeps an ocean of liquid water flowing beneath miles of surface ice. This hidden sea may contain more than twice as much water as all of Earth's oceans combined, and it's been stable for billions of years, more than enough time for complex chemistry to evolve toward biology. Dr. Kevin Hand, leading astrobiological research on Europa at NASA's Jet Propulsion Laboratory, describes the potential. Europa represents a completely different pathway to habitability. Instead of being warmed by a star, it's heated from within by gravitational forces. Instead of having surface oceans exposed to space radiation, it has a protected environment beneath its ice shell. It might be an even better place for life to emerge and evolve than early Earth. But Europa is just the beginning. Saturn's moon Enceladus has been photographed, spewing plumes of water vapor from its south polar region, direct evidence of a subsurface ocean that occasionally breaches the surface. Titan, Saturn's largest moon, may harbor multiple types of oceans, water beneath its surface, and hydrocarbon seas on its surface, creating environments for entirely different types of chemistry. The discoveries extend beyond our solar system's outer reaches. Even Mars, which appears barren and lifeless today, shows abundant evidence of ancient oceans that may have persisted for hundreds of millions of years, potentially long enough for life to emerge and evolve during the planet's early history. These cosmic oceans force us to reconsider everything we thought we knew about the conditions necessary for life. If biology can emerge in the subsurface seas of ice-covered moons, warmed by gravitational rather than stellar energy, then the number of potentially habitable worlds in our galaxy increases dramatically. Dr. Christopher McKay, a planetary scientist, studying extremophile organisms and astrobiology, explains the broader implication. Every time we discover another ocean world, we're essentially finding another laboratory where the universe might be conducting origin of life experiments. The same chemistry that created life in Earth's ancient oceans could be unfolding right now in dozens of different environments throughout our solar system. The chemical conditions in these alien oceans appear remarkably similar to those that existed in Earth's primordial seas. They contain dissolved minerals leached from rocky cores, energy sources from radioactive decay and gravitational heating, and complex organic chemistry driven by radiation and thermal gradients. The fundamental ingredients for life, liquid water, chemical energy, and organic compounds, exist in abundance. Future space missions are already being planned to directly sample these cosmic oceans. Spacecraft will burrow through ice shells, analyze the chemistry of erupting plumes, and search for the chemical signatures that might indicate biological activity. Within the next few decades, we may have our first direct evidence of life beyond Earth, most likely from the hidden seas of distant moons. But perhaps the most profound insight from studying cosmic oceans is how they illuminate the story of our own origin. By understanding how different environments might support the emergence of life, we gain deeper appreciation for the extraordinary chain of events that occurred in Earth's ancient seas. The presence of liquid water throughout the cosmos suggests that the chemical processes that led to life on Earth were not unique, isolated events, but part of a much larger pattern of molecular evolution that may be occurring wherever the right conditions exist. Earth's first oceans may have been just one example of a phenomenon that could be common throughout the universe. As we continue to explore these cosmic oceans and decode their chemistry, we're not just searching for extraterrestrial life, we're also learning more about the fundamental processes that create and sustain biology wherever it might occur. Each new discovery adds another piece to the puzzle of life's cosmic potential and helps us understand our own remarkable journey from chemistry to consciousness. Our next chapter returns to Earth to explore the greatest mysteries that still surround life's origins, the questions that continue to challenge our understanding and drive new research into the fundamental nature of biology itself. 4 billion years of detective work, and we're still missing pieces of the puzzle. Despite everything we've learned about life's ancient origins, the deepest questions remain tantalizingly out of reach, like trying to grasp water itself. In laboratories around the world, scientists are wrestling with what they call the origin of life gap, that crucial transition from complex chemistry to living systems. We can create amino acids, we can form cell membranes, we can even build self-replicating molecules, but we cannot yet bridge that final chasm between organized matter and genuine life. Dr. Sarah Chen peers into a bioreactor at Stanford University, watching molecules dance in conditions that mirror the ancient ocean. We're essentially time travelers, she explains, adjusting temperature controls that simulate a world 3.8 billion years ago. Every experiment is an attempt to witness the moment chemistry became biology. The water around her bubbles with the same volcanic intensity that once defined our planet. Inside, amino acids link into primitive proteins while lipids spontaneously assemble into membrane-like structures. It's hauntingly familiar. And yet something essential is missing. That missing element haunts origin of life research. We call it the information paradox. Life requires information, genetic codes that can be copied and passed on. But information systems require life to maintain them. Which came first? It's the ultimate chicken and egg problem written in the language of molecules. Some researchers believe the answer lies in RNA's ancient versatility. In Jack Szostak's lab at Harvard, synthetic RNA molecules are learning new tricks, catalyzing reactions, storing information, even competing for resources like primitive organisms. We're watching evolution happen in a test tube, Szostak notes, observing RNA sequences that have survived thousands of generations in just weeks. These molecules are showing us pathways to complexity that we never imagined, but even the most sophisticated experiments reveal how much we don't understand. Every breakthrough unveils new mysteries. Recent discoveries suggest that life might have emerged not once, but many times. Failed experiments in the laboratory of the early ocean. The fossil record offers tantalizing clues, but remains frustratingly incomplete. Chemical signatures in ancient rocks hint at biological processes, but interpreting them is like trying to reconstruct a symphony from a few scattered notes. Perhaps the greatest mystery is consciousness itself. How did the universe develop the capacity to wonder about its own origins? From water's first tentative experiments with self-organization to the moment you became aware of reading these words, the connection seems impossible. Yet here we are. Some researchers propose that consciousness emerged from the same self-organizing principles that created life itself. Water's ability to form complex, dynamic structures may have laid the foundation not just for biology, but for awareness. Modern neuroscience reveals that consciousness depends entirely on water's unique properties. Every thought, every memory, every moment of awareness requires water molecules facilitating communication between neurons. We are literally thinking with the same substance that first organized into living systems billions of years ago. The questions multiply faster than answers. Did life require specific conditions found only on early Earth? Or could it emerge anywhere liquid water persists? Are we alone in the cosmos, or has water seeded life throughout the universe? NASA's latest discoveries suggest that liquid water oceans exist throughout our solar system, beneath the ice of Europa and Enceladus, possibly in the subsurface of Mars, maybe even in the clouds of Venus. Each represents a potential laboratory where water might be conducting its own experiments with complexity. The Breakthrough Starshot project aims to send tiny probes to Proxima Centauri, where an Earth-like planet orbits in the habitable zone. If successful, we might glimpse oceans around other stars, and perhaps discover that water's creative potential extends far beyond our small blue world. But even as we search the cosmos for life's signatures, the deepest mysteries remain here, at home. In every drop of water lies the memory of that first moment when molecules learned to remember, to grow, to dream. The continuing mystery isn't just scientific, it's profoundly personal. We are water's way of asking questions about itself, the universe becoming conscious of its own improbable journey from cosmic void to living awareness. And perhaps that's the most beautiful mystery of all. Not just that water created life, but that life created the capacity for wonder. In seeking to understand our origins, we honor the 4-billion-year journey that led to this moment of curiosity. The questions continue as flowing and eternal as water itself. Right now, as you read, these words, ancient oceans, flow through your veins. Every heartbeat pumps water that once crashed against primordial shores. Every breath you take is humidified by moisture that may have fallen as rain when the first cells divided in shallow seas 3.5 billion years ago. This isn't metaphorical poetry, it's literal truth. The water cycle that sustains all life has been recycling the same molecules for billions of years. The glass of water you drink today contains molecules that dinosaurs drank, that nourished the first forests, that carried nutrients through the world's primeval oceans. Your cells are living museums of evolutionary history. The salt concentration in your blood matches that of ancient seas, preserved across eons of biological refinement. When tears flow from your eyes, they carry the same chemical signature as the oceans where your ancestors first developed the capacity to sense light. Dr. Lynn Margulis once observed that we never truly left the ocean. We simply learned to carry it with us. Every cell in your body floats in a personal sea, maintaining the conditions that first allowed life to flourish billions of years ago. Consider the miracle occurring in your body right now. Water molecules are facilitating millions of chemical reactions per second. The same fundamental processes that created life in Earth's first oceans teens fold into complex shapes guided by water's molecular embrace. DNA unzips and copies itself in aqueous solutions that mirror primordial pools. Your brain, the organ reading and comprehending these words, is 75% water. Every synapse firing, every memory forming, every moment of consciousness depends on water. Molecules carrying electrical impulses between neurons. Thought itself is a water-based phenomenon. Consciousness emerging from the same medium that gave birth to the first living cells. The connection runs deeper than individual biology. Human civilization has always clustered around water sources, rivers, lakes, coastlines. Our greatest cities arose where fresh water met the sea, echoing life's own origins at the intersection of different aquatic environments. Agriculture, the foundation of human culture, is essentially the art of managing water. When we irrigate fields, we're recreating the conditions that allowed the first photosynthetic organisms to transform sunlight into food. Every meal you eat represents water's continued role in sustaining the complex chemistry of life. But water's legacy extends beyond physical sustenance to the realm of imagination and spirituality. Every culture in human history has recognized water as sacred, fundamental, life-giving. From baptismal rites to meditation beside flowing streams We instinctively understand our deep connection to this elemental substance. The myths and stories we tell about water reflect ancestral memories encoded in our very DNA, tales of great floods, springs of eternal life, and water's transformative power aren't just cultural artifacts. They're cellular memories of our aquatic origins expressed through human consciousness. Modern science reveals just how profound these connections remain. Research shows that the sound of flowing water reduces stress hormones and promotes healing. Hospital patients recover faster when they can hear water features. Our nervous systems, evolved in aquatic environments, still find peace in water's presence. Climate change now threatens to disrupt the water cycles that have sustained life for billions of years. Rising sea levels, changing precipitation patterns, and ocean acidification represent challenges not just to human civilization, but to the fundamental processes that created and maintain all life on Earth. Yet water's legacy also inspires our response to these challenges. The same creativity that emerged from ancient oceans now drives innovations in water conservation, purification, and sustainable management. Solar desalination plants, atmospheric water generators, and closed-loop recycling systems represent water's ongoing evolution through human ingenuity. Children splashing in puddles after a rainstorm aren't just playing, they're expressing a joy that connects them to the deepest origins of life itself. That instinctive delight in water reflects our biological heritage, celebrating the medium that made consciousness possible. In laboratories around the world, scientists are learning to work with water as nature's most sophisticated engineer. Biomimetic technologies copy water's ability to self-organize, self-repair, and create complex structures from simple components. We're beginning to collaborate with the same forces that created us. The water flowing from your tap carries the accumulated wisdom of 4 billion years of evolution. It has nurtured every life form that ever existed, facilitated every biological innovation, and now sustains the most complex organism the universe has yet produced, you. Every time you drink water, you participate in an unbroken chain of life that stretches back to the first oceans. You are not separate from nature. You are water's latest and most remarkable experiment, consciousness emerging from the same creative force that first organized molecules into living systems. This is water's living legacy. Not just that it created life, but that it continues to evolve through us, creating new possibilities for complexity, awareness, and wonder. In the beginning, there was a question hidden in every molecule of water that rained down on the barren earth. What is possible? 4 billion years later, we are water's answer. We began this journey in the cosmic void, following water's path from stellar forge to planetary ocean, to the first stirrings of life. Now, as we conclude, we find ourselves confronting a question so profound, it changes everything we thought we knew about existence itself. The question isn't just how life began, it's why the universe seems designed for complexity to emerge from simplicity, for consciousness to arise from matter, for water to serve as the perfect medium for both processes. Consider the astronomical improbabilities we've witnessed. If water's molecular structure were even slightly different, if the angle between hydrogen atoms varied by just a few degrees, it couldn't form the complex networks that make life possible. If Earth's distance from the Sun shifted by a mere 5%, our oceans would either boil away or freeze solid. Yet here we are, consciousness emerging from complexity, complexity emerging from chemistry, chemistry emerging from physics, physics emerging from pure mathematics. Each level more than the last, yet each seeds of the next. The ancient oceans didn't just create life, they created the capacity for life to understand itself. In you, water has developed the ability to contemplate its own journey across deep time. Every thought you think, every wonder you feel, every question you ask represents the universe becoming aware of its own creative potential. This realization carries staggering implications. You are not an accident or an afterthought in cosmic history. You are water's way of knowing itself, the universe's method of examining its own reflection. Every act of curiosity, every moment of creativity, every expression of love represents matter transcending its apparent limitations. The story we've told, from the first rainfall to the first cells to this moment of understanding, reveals something extraordinary about the nature of existence itself. The universe doesn't just permit consciousness, it seems to move inexorably toward it, using water as its primary tool for creating increasing complexity. But perhaps the most profound mystery isn't how consciousness emerged, but what it means for the future. If water could guide the transition from chemistry to biology, from biology to awareness, what might consciousness create next? We stand at another threshold moment, not unlike those first molecules beginning to organize in ancient tide pools. Artificial intelligence, genetic engineering, space exploration. We're using the same creative principles that water pioneered billions of years ago, but now applied consciously, intentionally. On Mars, we search for ancient water signatures that might reveal whether life's story played out elsewhere. On Europa and Enceladus, robotic explorers prepare to dive through ice into alien oceans, seeking to answer whether water's creative potential is universal or uniquely terrestrial. The question that opened this journey, how water created life, has evolved into something far more profound. What is consciousness for? What is the universe trying to become through us? Perhaps consciousness is water's greatest invention yet. A way for the universe to experience wonder at its own improbable beauty. When you watch a sunset reflecting on water, you're participating in an act of cosmic self-recognition. The same substance that fell as the first rain is now capable of appreciating its own luminous dance. The eternal question reveals itself. We are not observers of the universe, we are the universe observing itself. Water didn't just create life, it created the capacity for existence to know and celebrate its own magnificent improbability. Every time you drink water, remember you are consuming the same substance that created you. Every time you feel wonder, realize you are water becoming aware of its own creativity. Every time you ask why, understand, you are the universe questioning itself through 4 billion years of accumulated wisdom. The first oceans asked a simple question: what is possible? Through billions of years of patient experimentation, water discovered that consciousness is possible, that love is possible, that wonder is possible, that the universe can come to know and appreciate its own extraordinary creativity. You are the answer to that ancient question. You are what became possible when water learned to dream. And the most beautiful part? The question continues. Water's creative journey hasn't ended. It's just beginning to understand what it might become through conscious, intentional collaboration. With the awareness it created, in the end we discover that we are not separate from the cosmic forces that created us. We are those forces made conscious, asking eternal questions about the nature of existence itself. The first oceans created life. Life created consciousness. Consciousness created the capacity to wonder, and wonder creates the future.